All right, folks, it's Bass Action back in action here. In this video, what we're going to do is we're going to look at how to build mathematical models to understand different relationships. It requires you to read carefully and know your library of functions well. Let's take a look at this first one to get a feel for how these are going to work. On our first problem here, it says that we're going to have some random point P that's going to be on the graph of y equals x squared minus 1. We're going to eventually write a function that shows the distance from a point on that parabola to the point 0, 2, and we're going to call that point P. So if we go to write this picture first, which is always going to be your first step, is to draw a picture. The first thing we want to draw a picture of is that parabola. You need to recognize that it's a parabola for starters. The next thing you need to be able to recognize is that it's a parabola that's simply been shifted down 1 unit. So this would be a minus 1. You should also very quickly be able to find those x-intercepts because those might be useful in different scenarios. So I'm going to go ahead and label those. You should be able to do those mentally. Now we're going to put our point P on our graph. It doesn't have to be perfect, as we've talked before. It just has to be generally in the right spot. So I have the point 0, 2. Now, if I have this point on the parabola that I call xy, we want to measure the distance between any random general point on the parabola and the point 0, 2. Our problem is that our ordered pair is written in terms of x and y, and in order for us to find a nice simple function, we want it to be in terms of one variable. Specifically, when we look here at A, it tells us that it wants us to be a function of x. So we need to replace this y with something in terms of x. And the original equation that we're given here tells us what to do. So I can rewrite this ordered pair. Since y equals x squared minus 1, I'm going to replace my y with x squared minus 1. Now my entire ordered pair is in terms of x's. Now I can go over here to part A and I can start actually finding my distance between these 2 points, the general point on the parabola and my point 0, 2. So I'm just following my distance formula. Remember, it doesn't matter what point we put first, but in this case it's going to be a little easier if we put the points that have the variable first. So I'm going to do x minus 0. Of course, that's going to simplify quickly. Then I'm going to have my x squared minus 1, and then I need to subtract the 2, and then that whole quantity has to be squared. Now, we're going to start cleaning this up and making this look a little nicer. So I'll have an x squared. Then I'm going to have my x squared minus 3. That's a quantity squared. Then I'm going to keep going. This next step, this is where students make some errors. When we go to expand this and get rid of our parentheses, we have to remember to FOIL. So we're going to have an x to the 4th minus my 6x squared plus my 9. If you don't FOIL, you're going to lose that middle term. Now we can finish and collect our like terms. And this would be our simplified expression with the parentheses all gone, which is how you will need to write this when you're doing it on a test. Okay, so what this function tells us is that if I pick a point somewhere along this parabola and I know its x value, it's going to automatically tell me at any different x value how close I am, what is my distance away from this point 0, 2. You can type this equation into Desmos and you can see how close it could possibly be, and we're going to do more of that in class. So on this part B, what we want to know is if the x value is 0, in other words, if I'm right here, x is 0, how close am I? Now, obviously, we could mentally calculate this one ourselves, which is part of why we're doing it. We're choosing a number that we know well, that's going to be easy to do mentally to help us understand how this formula is going to work. So we're going to pick an x equals 0, and we're going to see. We should be expecting this answer to be a 3 when we plug this in. So when I go ahead and I find this distance, if x is 0, all the x's are going to drop out, so I get a 0 minus a 0 plus a 9. So sure enough, I get a distance is the square root of 9, which is 3 units, which is exactly what we wanted it to be, and we could see on our graph. Now we can also do it if x equals 1, so we could do another one just to, get a feel for what's happening here. And if I do x equals 1, then I'm going to have a 1 just subbing into my function that I have right here. I have a 1. Now I'm going to have minus 5 plus a 9. So that's going to be the square root of 5, which we wouldn't know that number perfectly, but we do know it's going to be something a little more than 2 because square root of 5 is a little bigger than square root of 4. So if I was right here, at x equals 1, this distance would be the square root of 5. Okay, so this is just a first dipping our toes into this. We'll do more with this when we get into class and look at the graphs. So let's look at one more that we could go ahead and draw. This one has a few more instructions. This one says that we want a rectangle. It's going to have one corner that's going to be in quadrant 1, specifically on the graph of 25 minus x squared. Then it's going to tell us that another corner of the rectangle's at origin, and then another one's on the positive x-axis, and a fourth is on the positive y-axis and a positive x-axis. So let's start with our parabola first. And again, you have to be able to quickly recognize that that's a parabola. This parabola that we're working with this time is a downward turning parabola that's been shifted up 25. I'm not going to draw this to scale. I just want to get this generally to make sense. So that's going to be a 25. Remember, I said that you want to be able to mentally be able to quickly calculate those x-intercepts because those are going to be important for us. So I'm going to have a -5 and a 5. Now I can start drawing in the rectangle. I can't draw the rectangle if I don't have the parabola first. It says one corner needs to be on the parabola. So one corner is going to be right there. Another one's going to be at origin. This is supposed to be a rectangle, so it makes sense that the point that's on the x-axis is going to be straight down, and the point that's on the y-axis is going to be directly over, so that makes a nice rectangle there. Now, if this ordered pair right here is an xy pair, and again, just like before in part A, we ultimately need to write it as a function of x. So I need to get rid of that y value first. I'm going to go ahead and I'm going to, instead of writing xy, I'm going to write x, and then I'm going to write 25 minus x squared. You've got to get rid of that y from the very beginning. Now, we ultimately want to be able to find the area of the rectangle. So we're going to need to remember that area of a rectangle is base times height. So when we come to our picture, we're going to label our base and our height. So that side would be x because we're thinking, how do I get to this point? I go over and up. And I went over an x, and the amount that I went up is that 25 minus x squared. These are the two numbers or expressions that we'll use to find our area expression, our area function. So now I can say area in terms of x is x times 25 minus x squared, and then I could simplify that. Both the factored and the non-factored form are useful for us. 25 minus x cubed. So that's our function. So if you could type this into Desmos, and then what we will be able to do is we'll be able to maximize the area of this rectangle and figure out what is the largest rectangle that we could draw that's inside this parabola, which then leads us to this implied domain. Okay, if we want to draw a rectangle inside the parabola, what we need to remember is that the sides have to be positive. Okay, so when we're thinking about any rectangle, the sides of our rectangle have to remain positive, and then also we need to remember that it has to stay inside the parabola. Okay, now In order for us to have positive sides and for it to stay inside the parabola, that's where these x-intercepts are important to us. It means that I can't choose an x value bigger than 5 or I'm going to go outside the parabola. I also logically can't choose an x value that's negative because that's going to violate my original requirements and it would give me a side length that's negative. So our implied domain for the function is going to be 0 to 5, and we're going to use parentheses because we can't actually include the values of 0 and 5. This implied domain is important to talk about implied because if we're just looking at this function right here, we can see that its domain should be all real numbers because there's no fractions and there's no radicals. So the concept of implied is really important, and you're always just going to have to look and think about the problem.